Okay, I'd like to look real quick just at the conservation of momentum. Momentum is a conserved quantity. Um, we can kind of think of there being initially zero momentum in the universe, but since momentum is a vector, there's positive and negative values, and everything's got some momentum running around doing its thing. Effectively, if momentum is conserved, much as mass energy is conserved, then what we can really say is that in a system interaction where something pushes on something else or hits something else, you're never going to gain nor lose momentum. The momentum is just there. It's conserved. So what we can kind of say here is that in some sort of interaction, the change of momentum is going to be zero. And what this means is that the final momentum minus the initial momentum, because remember, delta always means final minus initial, equals zero. And what this means, if I just kind of swing the initial to the other side and then do a flip move on it, this means that the initial momentum has to equal the final momentum, which if it's conserved and we're not losing anything, of course it has to. You knew that. So this is an important thing for us to recognize. Now, what this means for us, though, if the initial momentum and final momentum are equal, is that if we have two objects, and these objects each have their own momentum, such as, I like to play with penguins in my life. That's just how I've always played with physics. We'll call this little guy Gunter. That's a bad penguin, but oh well. We'll call this little penguin over here Gunther. He's a different penguin, but very similar. Then, if these penguins are each moving at each other with some velocity and have some mass, then when they collide or interact with each other, the mass and velocities they have coming out of the scenario, well, the momentums have to be conserved. Because of this, if we have object 1 and object 2, for the initial and finals, we actually have a rather long equation that's not difficult to use, but it's just a lot of writing. And it kind of looks like this. We know momentum is a mass times the velocity. So the mass of object 1 times the velocity of object 1 plus, and these are initial quantities, plus the mass of object 2 initially times the velocity of object 2 initially. These are our initials. Equals the mass of object 1 at the final state times the velocity of object 1 at the final state plus the mass of object 2 at the final state times the velocity of object 2 at the final state. Now, normally for the masses, you're not going to gain or lose mass, so you don't really have to worry about it. There are some scenarios, such as if you have a rocket where pieces come off of it, your masses could change. But in most cases, your objects are just your objects. So you're not really worried about an initial or final mass. But this is our big equation here. It's basically saying that the initial momentums added together equal the final momentums added together. And that's it. So you can kind of do cool stuff with this. Right now we got the Olympics going on. So, if you imagine, and if you've seen Blades of Glory, this is a wonderful scene where two figure skaters are standing hands together on the ice and they push each other apart. So let's draw that just for a laugh, right? I'm a bad drawer. We take figure skater 1, figure skater 2. You have to be standing in a cool way. This guy's got the red cape on. Put the blue cape over here. Okay, if they're standing there initially, their initial velocity is 0. So right off the bat a lot of information about this. If both of their initial velocities are 0, then everything on the left side of this equation, m times 0 plus m times 0, is 0. Cool. That has to equal, after they push off, all of the final information. Now, let's give these people some masses. If the mass of this skater is, I don't know, let's go 50 kilograms. and the mass of this skater is, I don't know, 40 kilograms. Then after they push off, if we're able to measure this skater's final velocity as negative, because we'll say as this skater's pushing off, he's going to the left, the negative direction, and that's very important. Since direction matters so much here, we need to pay attention to that, because we're going to see it pop up. Let's say he's going to negative 10 meters per second. Well, what's the velocity of our second skater? Well, we can get that pretty easily. We're just doing mv plus mv. So for our first skater here, mass of 50 times negative 10. Okay, plus 40, the mass of the second skater, times, well, we don't know what the VF is for that. If we go ahead and solve this, we're going to get 0 equals negative 500 Newton seconds plus 40 V2F. Doing a little bit of math, we'll add 500 to each side, and then we'll divide by 40. So we're going to get positive 500 equals 40 V2F. Divide each side by 40. And we find that the velocity of the second skater in the final state is equal to 500 divided by 40. Throw that in real quick. We get 12.5 meters per second. We get a positive number here because this skater, when they push off, is going to go in a positive direction. So that makes sense. It also makes sense that since this skater is less massive, whenever this push happens equal and opposite. So when this change in momentum occurs for each of them, because the blue skater here has less mass, they're going to gain more velocity. That force is going to impart more motion onto their system in terms of their speed. So the lighter object will move faster, and that kind of makes sense. Okay? So this is just a conservation of momentum. It's pretty straightforward. There are some little tips and tricks that go along with it, such as in this case, if you start at rest, then everything in the beginning is 0. If objects end by colliding and sticking together, their values are 0. Sometimes we have a scenario where an object bumps and one object stops and the other goes. If it stops, its final is 0. And sometimes, and these are interesting cases, you have an object strike another, stick to it, like a thing of putty or something, and then they both move together. And in that case, they both have the same final velocity. And those are actually like terms. In that case, you'll have 2 objects in the beginning moving, but only 1 object in the end. That object in the end just has the mass of both of the objects there. Those masses are added together. So that's kind of an interesting problem there. But in the end, it all pans out the same way. You're just using over and over and over again this rather long equation, but it's very straightforward. The initial momentum equals the final momentum. So with that, that's a conservation of momentum. That's over.